So it's an absolute privilege having Cam McCuaig here with us today. Cam is currently the Head of Geoscience Excellence in BHP's Resource Centre of Excellence. Cam's career has taken him to 43 countries on 6 continents, working in a wide variety of commodity systems and mineral deposits. So with his extensive career, I'm so grateful that he'll be chatting with us today about geoscience vision for future resource exploration and extraction. So it's going to be an awesome session. Please use the chat. You'll have the chance to jump off mute and we'll have some discussions at the end of the presentation. And yeah, I hope you all enjoy it. So thank you so much, Cam, for joining us.
First of all, thanks to Jess for the invitation to present to the GeoHug community. Just a fantastic effort that you've been doing, Jess, getting these talks together, and really the following that you've generated. So real kudos to you. And today I just wanted to have a bit of a chat about where geoscience may be heading in the exploration and extraction side of the business. In fact, at the moment there's been a lot of press around and a lot of literature coming out on the plight of geoscience, if you want. And we've seen that act out in Australia in terms of departments being shut. Australia's not an orphan there. This is happening in a lot of the developed nations around the world. And so hopefully this will be a bit of a timely visit of how some of these trends might impact on geoscience in the future and the types of geoscientists that we'll want into the future. I should also mention that this talk was originally given as a keynote at the SGA conference in Glasgow. So I'm essentially reproducing it here. I just wanted to acknowledge that it's been presented before. So this slide at right has a diagram that looks at some of the forces that are acting on our industry. So you can see that, look at thinking about things that are within your control in your company, your transactional environment for any resource company that we can influence, and then things that come at us from a contextual environment of society and megatrends, et cetera. And so these are the things that really control us, that we have to be ready to react to. And at left, I've just pulled out a couple of those that maybe we could talk about a bit more. And one of them is the fact that we've got an increasing population and we've got an increasingly tech-dependent population, and that is going to increase, that acts to increase resource demand. So even though that there's talk to moving to a circular economy, people forget that there is a second law of thermodynamics, which essentially translates to you can't get something for nothing, and that you never get all of it back. So the idea that we're going to rip up all the copper cables on Earth, that's how we're going to get our copper or something, is just not going to happen. So, and also the fact that the usage of metals per capita is going to go up anyways, even if you don't have an increasing population, which we almost certainly will. Second thing is again getting more and more airplay, and it's translating into how investors are reacting, how universities can partner with companies, and that is social pressures for environmental stewardship. And that really that actually puts a downward pressure on resource supply. It restricts the supply, and we'll talk about that in a bit, talking about how that's going to redefine ore for the industry and for society. Other trends that are coming at us, of course, data. Everyone's talking about AI, a data-rich future, and you think about where we are now, where your mobile phone has about, well, at least 100,000 times more processing power than the entire Apollo 11 mission, which 52 years ago put the first people on the moon. That's pretty amazing. And you look into the future, and I can just imagine my grandchildren will end up looking at me and saying, really, you had this separate device, you just didn't tap the chip in your temple and download it from the cybersphere? So, no. So how's data going to change us in the future and how we work? Increasing automation, technology advances, the ability to take people out of the line of fire, and it is going to change the structure of the business in terms of where people work, where geoscientists work, and what they do. A lot of unknowns. What's the commodity mix of the future? So I think what's going to replace the energy density of hydrocarbons, for example. Ask different people, you'll get different answers, but the reality is we'll still be extracting something. Humans are an extractive species, we always will be, and that'll require geoscience. And then another one on top of that is geopolitical constraints. At the time this presentation was first constructed in 2019, we were in the middle of a nationalistic wave that was sweeping across the world, across the globe, Brexit, and et cetera, and other such actions around the world. And then you put on top of that the pandemic that has happened since then, and you have a real issue with access to resources, right? With the uncertainty in the world at the moment, the geopolitical uncertainty, and also with geoscience mobility and where you can source talent. So with all that as background, we can think about how those trends, or how some of those trends and other trends will impact geoscience in the resource industry. So on this slide, what I've done is I've broken down the value chain into essentially 4 rough bins. The first one being exploration and discovery of resources. The second are where we actually delineate these resources, we model them, we plan them, through to say feasibility study. And then the extraction side of the business. And at the end, of course, the one that people tend to kick down the road and not think about is closure. At some point, mines have a finite life, resources have a finite amount. And at the end, how do we have proper stewardship to manage when they do come to an end in terms of a productive life? And also the bars at the bottom are the relative proportion of the approximately 650 geoscientists that work across BHP in there. Now, depending on what audience you talk to, a lot of times when I'm talking to external groups, I'm talking to people that work more on the research side or the exploration side. And a lot of times they're surprised to see this bar graph, to see that there's so many that sit in the resource appraisal extraction side of the business, and the opportunities in geoscience to really have an impact in those places. And the one that's most disturbing in general, and certainly BHP is not an orphan in this. This is throughout the industry. That relative bar of closure is alarmingly small, but guaranteed it's going to get bigger in the industry as a whole into the future. So I'm just going to talk through those in sequence, essentially, and just to prompt some thinking. And I'm really looking forward to the discussion that comes after this presentation on how those areas of geoscience in the resource industry could be impacted. Now, I'm not the first to talk about the exploration challenge undercover, nor am I the first to show this diagram at right. I'm sure Robbie Rowe would be very familiar with it, and I saw that he was on the call. And so the map at right shows in the colors the depth to economic basement, although that varies of what's economic. Sometimes there are resources in those cover sequences, which is a separate discussion. The other thing it does show, though, is it shows the deposits, and it shows the deposits as compiled by Richard Shoddy of MinEx to the top of the discovery, so the top of economic mineralization. And there's almost a one-to-one, with very few exceptions here. There's a one-to-one relationship of mineralization with outcrop or subcrop. And our exploration technology package is actually optimized. You know, we've become better and better and better at finding mineralization. If it outcrops, or if at one point it outcrops, and then we can see the residual of it through erosive processes. And the challenge we have into the future is that there is a lot of wealth that is sitting underneath that cover. And I think, you know, a lot of people will acknowledge that. The challenge is, how do you go and find it and delineate it and then mine it? The economics of the mining isn't actually what stops us. Is it a challenge? Absolutely. But it's not what stops us. The big finds in these areas would be economic. It's the cost of finding it and delineating it. And that's really the challenge. So if you add on top of that the layers of ground access becoming more challenging, social license to operate being more challenging, it means we've got to be that much better at determining where we are going to go do this higher risk but high reward exploration. So if we think again about that discovery side of it, the diagram in the middle is an attempt to break down the elements that come together to form any type of mineral system across a range of scales. So from left to right is meant to represent more of a global scale, where you're trying to select where is the sedimentary basin or the continental or volcanic arc that you want to go play in. Which one do you want to go into? The second box is more around the camp scale decision. Where do I think that there's a concentration of mineralization where I want to go and pick up contiguous packages of ground so I can systematically explore them. And the third one, the prospect scale, is about, okay, where do I think the deposit is? Where's the value that I'm trying to realize? On the left-hand scale we've broken the mineral system down into 5 key things that have to come together for any system. Number 1 is fertility. I need to have the metal. I need to have a source of where that metal came from. And I need a transporting agent. That transporting agent can be a magma, it can be a fluid, but something that helped move the metal from its source to where eventually it's going to accumulate. The geodynamic trigger speaks to the fact that ore deposits form relatively quickly on geological timescales. So there's generally correspond with big geodynamic changes that turn a geological system into a mineralizing system for a brief period of time. So identifying those triggers, the architecture of the system, the geometry of the system, which includes pathways and for the transporting agents and the metals to move around in. The site of deposition, what's actually causing the metal or to accumulate, or the petroleum to accumulate, if you want to go into the petroleum side as well, because this is equally relevant for any commodity. And then you have to preserve it to be able to come across it in the future at an economic depth. And the colored areas show the relative areas of focus. So, you know, ideally at the scale of the planet, you'd be able to just be in space, have a satellite and go, there it is, just like they used to do in Star Trek. You know, here's the dilithium deposit and I can detect it and I'll just beam it into the hold, right? And the challenge is that at that global scale, we don't have a direct detection technology. There's nothing that can tell you this is where the next deposit is. So when you're at that scale, you're not worried about actually directly detecting the deposit, or you're just setting yourself up for failure. You're worried about de-risking the presence of the mineral system. Are the elements of the mineral system actually present? And so you're focusing a lot on the things that are larger scale. When you get down to the prospect scale at the right-hand side, now I'm worried about where the deposit is. And now I'm into more traditional, if you want, though it won't be traditional in the future, detection technologies. About, okay, now I'm actually trying to delineate the deposit and where it is. And so as you go through this, there's different tools that you use at different scales. And some of the ones that we need to use in the future are non-traditional in our current technology package. For example, looking at paleoclimate, as well as plate models and timing of deposition and loading of sediments in sedimentary basins as depicted by the three globes up at the top left, to understand things like how brines are being generated and moving around in sedimentary basins that then control metal movement in sedimentary basins. At the bottom is some indicator minerals. So, and there's a lot of work being done in this at the moment, where we can actually progressively, we're getting better at detecting the fertility of different belts for different types of mineral systems, so that we can use nature's concentration process, rivers, find these minerals that are resistant to erosion, sample them, look at their chemistry, and if we think we have representative samples, then be able to screen and eliminate parts of the globe to determine where we want to focus exploration efforts in. When you get to the camp scale, it's going to be much more about using geophysics to map elements of the system, to hone in on where we think the focus of mass and energy transfer is, that has brought the metals to a site of potential accumulation. And when we get down to the prospect scale, this is the type of diagram that most geologists are familiar with from an economic geology text, which is about the footprint of the deposit at the deposit scale, which is essentially what is the expression of heat and fluids interacting with the rock around the site of deposition and being able to vector in there. And there's a lot of research going on at that scale, and progressively there's more and more research looking to those larger scales. So, you know, that technology package that allows you to use the appropriate tools, get the appropriate data to generate the appropriate knowledge across a range of scales is being developed, and different people and different companies are at different stages of that journey. But it'll be exciting as to where that leads. The other thing is the ability to get data. People look at that picture on the left and this is for a geophysical survey. And people say, oh yeah, that's what we used to do 50 years ago. Well, actually, that's what we've done in the last decade. You know, people still are doing surveys like this. It's taking weeks or more to be able to get access to the area in terms of permission. Then it takes days to get access to actually physically access the area. And then it takes literally minutes to get the readings sometimes. And so that how do you get more efficient data acquisition? And there's a lot going on in that space. The top is showing drones that drop seismic receivers, and they can drop up to 4,000 a day in rugged terrain. They self-couple with the ground, and because you drop so many, it doesn't matter if they fail. They're designed so that they're largely biodegradable, and you then can bring in sources and do your seismic survey, and you don't have to cut massive amounts of lines through rugged terrain. At the bottom, another example of using drones as receivers, so that you can then move your source over top, and then you haven't disturbed a lot of the land. You've simply flown in the receivers and parked them and coupled them with the ground. And these are just some examples of how, we're moving to more efficient data collection. And with this also comes a focus on increasing the quality, sensor technology to be able to do multiple surveys at once. So this is going to change our ability to acquire and use geophysics at a range of scales. One aspect of the exploration undercover challenge is being able to see the unseen and also quantify what's down there. Not just make a cartoon image of it, but actually be able to quantitatively model the Earth. And an example, this is where we could learn from our petroleum. So most of the people on this call will be minerals people, but this is where we can learn from the petroleum side of the resource business. They've been in this challenge for some time where they, one of those wells, you look at that oil well that's sitting there, that type of well in the deep basin might cost $250 million, $250 million to drill that well. So they have to think pretty heavily about where they're going to put it. And they've developed techniques to get the data they need, and then they marry the geophysics through really strong petrophysics to the actual geology and geomechanics that they want to know about how, A, what that rock mass looks like, and B, how that rock mass is going to perform as they start to draw fluids from it. And this is an example of a challenge of seeing below salt. So that was in the Western Gulf of Mexico. That's been the big limiting factor, is a lot of the plays are under pretty continuous salt canopy. And so how do you see below it? Because it's really hard, it's very complex, hard to model beneath. And so they designed a way to use ocean bottom nodes and design the surveys and do the processing to be able to do this. So that was quite revolutionary. And that happened within the last decade or so. So when we get more of this data, then a lot of talk is about AI and how AI is going to change the business, and it is because what machine learning is doing for us now is the ability to query multiple data sets at once, large data sets that the human mind just would never be able to do in a systemic fashion, and realize correlations. The idea though is how do you use AI to maximize human intuition but minimize human bias? You don't want to take the human intuition out of it, because the human mind can do a lot that the computer still struggles to do. So the idea is that you get the data. AI helps you at the moment recognize the patterns, and then it makes you think, okay, what's the process that underlies that, which then points you to what's the next data set I should get. And you do that iterative, inductive, deductive loop. And that's becoming faster and faster and very much more powerful. The top end of the pyramid, where the computer actually asks the questions and formulates the hypothesis, we're still a ways away from that. I mean, that would be the ultimate in terms of AI, but we're still a ways away from that. Just wanted to make a comment on the external pressures of carbon footprint, also socioeconomic footprint, physical footprint of our mines. When you look at the mines that have won in the future, a lot of them are, let's call them low grade, large tonnage operations that are incredibly energy intensive. In the future, one could question whether these are going to be the winners in the future, because in the future, we're going to need to be, we're moving into an energy constrained world, into a world where we're trying to reduce our carbon footprint. And to do that, what we need to do is we need to be able to get more extractable metal per kilowatt hour, per ton of water used, per ton of CO2 produced, per ton of waste or tailings produced. And then when you look at how the industry is actually exploring, a lot of them are still exploring for these or trying to develop these large, low-grade, energy-intensive, water-intensive operations. And so there's a bit of a disconnect there between maybe, this is personal opinion, right? About what we want in terms of what determines a quality deposit into the future. So just something to think on there. Moving into the actual delineation and modeling of deposits, we're seeing a lot of automation come in. We've got automated rigs now where we can, we're running these remotely. We're taking people right out of the line of fire. Not only that, but we've got a lot of tools that we're putting down the hole. We're getting lab at rig. We're getting a lot of information in near enough to real time, so that we've got these fire hoses of data coming at us that we're going to be struggling to swallow. So our ability to generate data at the moment far, far outweighs our ability to fuse that data together and into the knowledge that we require to make the business decisions. And this is more and more, this real-time modeling, being able to inform the data collection as it's happening will be the way of working. We also have all types of techniques to gather that data now. These are examples of visual optic on the bottom left. And then you've got hyperspectral that you can use to map these exposures, and then generate models of the rock. So we're getting lots of data that we can integrate. But our challenge still is, what's behind the wall? So, we can, on the exposed surfaces, we can get lots of information. From the drill holes, we can get lots of information. But we're still struggling to see the unseen and quantify the unseen behind the wall to deliver not just resource, but reserve, geology to reserve. How's that rock going to perform as we break it, move it, treat it by some physical or chemical process, produce a super high quality, consistent product that we put to port, and sustainably dispose of the 99% of the rock mass we don't want, right? And that's where really bringing in some of the stuff we were talking about before, bringing in a more clever use of geophysics to go from understanding pencils in space and quantifying pencils in space and using geological rules to join the dots and geostatistics to join the dots, to actually quantifying, measuring and quantifying volumes of rock, and using drilling to test our models rather than to build our models. I think that's really the aspiration into the future. And this example at Olympic Dam from one of our rock stars, Kathy Ehrig, who would be well known to a lot in the audience in this presentation. Kathy's one of the top geometallurgists that on the planet, and at Olympic Dam, they actually can model in the resource model. They've got proxies that they can build that actually tell you how that rock, that volume of rock is going to perform all the way through that process. So they can actually put a dollar value onto it. So they do some remarkable stuff there in terms of geometallurgy and quantifying performance of the rock mass through the mining process, not just a resource model of tons and grade. And in closure, people are aware of numerous examples where there's been challenges in terms of closing operations and the environmental legacy that's left behind. And one of the challenges we have is in society, communicating out to society. what they see is they see the mines of 150 or 100 years ago. And that's the image they have of mining. They think how we mine today is what they're seeing from 50 or 100 years ago. And that isn't really the case. Today, when we open mines, as an industry, we're actually thinking of closing them at the same time, right? And now there's still a ways to go in that space, but we are getting better and better at that. And so we are moving to look at how do you make mining value additive through the entire process, right from the exploration stage, through the mining stage, when you've got the community there, right through to post-mining, so that it's still a value-adding aspect after mining has stopped, that we have actually added value to the land and the communities, that is a legacy that lives on in a positive sense. And I'll finish off a little bit on ways of working. When you look at how we work today, a lot of people still would be familiar with what we've got on the left-hand side here. With we've got some screens. We still put a few maps out on tables. To moving an actual interactive interpretation on screens, and into the future. The picture at right, and I'm not sure how well people can see it, but in sort of the bottom left hand, you see a couple of surfaces. That's actually a holograph. So you're seeing it through somebody's goggles. That's a holograph that you can actually rotate, spin around. You can voice command faults on, faults off, surfaces on, surfaces off. And you've got, in this case, there's those four people, plus the person with the goggles. You've got 5 people interacting with the hologram, right? And these are things that are actually happening today in terms of how we interact with models and be able to walk through them in 3D. So you can envision a future where people are actually, you've got a holodeck. People are actually coming in, and their avatars are interacting with each other real time with the data, even though they could be sitting in offices in Houston, Perth, mine site, and they can all be working in the same space. And really, this is the type of collaboration we could be looking at in the future. A last note on inclusion and diversity. And there's 2 aspects there. Diversity, which is making sure you have the right range of voices in the room. And why do you want diversity, right? Diversity to represent your population, absolutely. But you also want diversity because you want diversity of thinking. Because to get the best outcomes, you actually need that wide range of opinions. And so you want a diversity of thinking. So to have a diversity of thinking, you have to have a diversity that represents the diversity in the population. Right? So that's to me, that's a big reason why I think of wanting diversity. The other thing, though, is inclusion. And there's a difference between having a diverse team and an inclusive team. And just a reflection, one thing I've found with the pandemic is when we started to do things like Miro boards and work on Miro boards, what I found was that it was way more inclusive, because people that would normally sit quiet in a room where maybe 2 or 3 dominant voices would dominate in a workshop format where everyone's physically present in a room, all of a sudden you found that these people were speaking up and their cursors were going all over the screen and they're throwing sticky notes everywhere. So it was actually really cool. I think something we've learned in the pandemic, forced into that online virtual collaborative workspace, is actually a way to unlock inclusivity to some degree. Just a little reflection on that. So we actually, even in a world where we would have a face-to-face workshop, we still look at setting up those virtual spaces because we see that people unlock a little more in those virtual spaces, sometimes when they don't in a face-to-face. So trying to combine the best of both worlds into the future. So this is the last slide. I don't know how I've gone on time there, Jess, but just looking at what the future looks like. First of all, the move from quantitative, drawing the cartoons and the high risk coloring in that we used to do when I went through, because color meant it was permanent, right? When you put the colored marker on when I was in university, to really that quantitative modeling. The interconnectedness, diverse, inclusive that I just finished off on the last slide. I think exciting. It's going to be more high level thinking. A lot of the labor intensive aspects of the job, particularly on the extractive, on the resource appraisal and extractive side, a lot of that labor intensive work will go away, and people say, oh, we're going to lose geology jobs. No, you're still going to need the geologists. They're just going to be working differently and thinking differently and thinking at a higher level. They're going to be knowledge workers, not data collectors, right? And I think that that's exciting. So we're going to be capability and capacity challenged in terms of the ability to source talent, especially with the restrictions we talked about with nationalism, the uncertainty in the world today, the pandemic overlay at the moment that still continues. So how do we ensure that we've got the capacity of geoscientists, but also the capability? How are we going to train geoscientists in the future? If you look at university programs, some of them haven't changed an awful lot since I was a student. Now they have in a lot of ways, so how do we train them into the future? And so to future-proof yourself as a geoscientist for the people, the younger people, I guess, on the call that are looking to the start of their career, really making sure you've got that strong science, technology, engineering, and maths background. That quantitative analysis will be really imperative, but also critical thinking, the ability to undertake critical thinking is going to be necessary. You're going to have to invest in a journey of education. There is no university that will teach you how to be a top resource industry geologist. It's just impossible in the time frame. The university gives you a solid grounding, and from there, it's up to you. Right? And you're going to have to invest in continually learning. And I think you see that the people that are really successful over time in the resource industry have done just that. They're professional students, essentially. Taking interest and awareness in the entire resource value chain. I've shown you the whole value chain here. It's not just about discovery. It's about asking the engineers and the mine planners, what keeps you awake at night? When you wake up screaming at 2 a.m., what's going through your head? And then for getting into their head about what matters, and that lets you take the geological knowledge, build it better, and deliver it better to them. And that leads into the soft skills in terms of the communication, being able to interact, network with other people in that space, because it's all about interconnected teams and integrated teams, not just about geoscience in the future. And I'll leave it at that. And hopefully there's some really good discussion and even challenge on this from the audience. I saw some of the faces I recognize, and I know there's a few that I'll tap on the shoulder if they don't speak up. Thanks, Jess.
Thank you so much, Cam. But yeah, I really appreciate you taking the time to chat to us. So thank you so much. One of them that's come through, there seems to be an assumption, as you stated, that under deep cover is as prospective as outcrop or near surface. Is there evidence to support this, or is it potentially an extremely expensive fallacy?
A good question. I think there's areas where you can project. The easiest one is where you can project mineralized areas undercover and say, look, we don't know how much is there. It's not like we can say, okay, there's X ounces of gold or there's X tons of copper in that area, but that it's prospective and that it has all the earmarks of potentially having large concentrations, right? So that the value could be there. Does that guarantee it's there? No, right? And that's why it's a challenge, right? But there's other areas that don't even outcrop, that have all the earmarks at a large scale of potentially having a large system. Examples, we have examples in Australia, like the Olympic Dam area, right? It's all undercover, right? Now, are there large deposits there? Yes. Has it been a struggle to find them and economically mine them? Yes. But are they really big option value if you unlock them? Absolutely. Like Olympic Dam is one of the world's greatest ore bodies, right? The challenge has been turning it into the world's greatest mine. That's been the challenge, right? But it can be done. There are other areas like that too, where the terrain actually doesn't outcrop. When you're looking at, we're looking at some stuff east of the Yilgarn for Cratton margin nickel. And do we know the nickel's there? No, we don't. Does it have all the earmarks at the moment of a potentially a big system? We think so. And we're trying to de-risk that. Where do you find the analogous rocks? Well, they don't outcrop anywhere in the Australian continent. The nearest outcrop's probably somewhere in the Arizona, in uplifted areas in Arizona, because that's where Australia used to be connected, right, at the time. So that type of exploration is more challenging. Now, so is it a fallacy? Maybe time will tell. Do I think so? I don't think so. I think there's a lot. I mean, it would be a pretty massive coincidence that all the economic mineralization is within areas of the earth that is in outcrop or subcrop. That would be a pretty impressive if that ends up being the case.
Yeah.
I don't think it is.
Thanks, Cam. There's some more coming through. Ore reserve quality is key. I agree that we must adapt to mining smarter, not larger, with the future in more selective mining. Interested in your thoughts on a few questions around this. So question one, how do we integrate critical ore quality ingredients during mineral systems analysis? Is it possible or dependent to each deposit once discovered and analysed in detail? That is a time-sensitive part of the bigger picture that is talked about lots.
Yeah, at the AusIMM conference in 2014, there was a keynote on exploring for quality. That's a good start. Yes, you can explore for the probability of quality. So you can say this area has the potential for large and for size and quality. Now the quality is multi-parameter space as well, and what makes quality will vary slightly by jurisdiction as well. But yes, I think you can explore for the probability of higher quality material. But at the end of the day, it will come down to there will be a lot of stuff site specific, deposit specific, that determines absolute grade, etc. At the end of the day, mineralogy, gang and host rock issues, all those types of things.
Yeah. The second question was, quantitative mineralogy, in my opinion, strongly underpins quality assessments of all reserves. What do you think is holding industry back from plunging headfirst into this? Cost, data, cost, data, limitations, ignorance.
Yes. Definitely cost, and to some degree ignorance. So there is a creative tension between optimizing the now and getting what is seen to be a super cost efficient, effective machine running in terms of mining a resource and optimizing the extraction of a resource, versus investing in knowledge earlier in the process, right? Now, and so what happens is that if you're asked to cut budget, what happens? Well, you have to cut a drill program. You have to do, maybe you have to lose a few full-time equivalent people, right? So, and then, you ask yourself, well, was that program useless? Were those people just sitting around twiddling their thumbs? And the answer, of course, is no, right? So, but you had to do that to cut the costs. And then we say, okay, look, we're a much leaner machine. See how good we are. What we're not really doing, though, in that process is saying, what is the risk that we introduce to the business by not getting that knowledge, that data and knowledge up front, right? So there's one aspect that the people managing the operations, right? They're measured on yearly performance, 2 yearly performance, that they're being asked to be ultra efficient, right? The knowledge investment up front often won't have a payback until beyond your 2-year plan, into a 5-year plan, or even beyond that. So it's tough to align those. So I just like you have the first law of thermodynamics, which means you can't create matter. Can be matter and energy can't be created or destroyed, right? You have to balance them. There's the first law of corporate dynamics too, in my mind, which is it's the law of risk cutting balanced against, cost cutting balanced against purchasing risk. So I think as geoscientists, what we're not good at is when we cut knowledge generation up front. What we're not good at is communicating to the business by not getting that knowledge up front. We've introduced this risk to you, which is going to eventuate in these potential ways. And then it's a decision. The company may decide we're willing to wear that risk and firefight at the back end versus the upfront knowledge, or they go, no, we're uncomfortable with that. We're going to need to invest in the knowledge. And that's where, as geoscientists, I think we need to be better at being able to really communicate into that corporate level about front-end loading. Geoscience knowledge can have a massive payback if done well.
Diversity and a wide range of experience and opinions in a team are both essential, but how does diversity differ from the term inclusivity?
Okay, diversity. I'll give you an example. I can have a really diverse team. I can have every nationality. I can have neurodiverse people. I can have basically pick a segment of society, and I can put them all in a room, right? And then you put them in a room with 3 loud voices, or people that are hierarchically higher, and all of a sudden, a lot of those other people, right? No matter where they come from in that diverse range, are quiet, right? Now you've got a diverse team that has no inclusivity. And at the end of the day, the decisions you get, you might as well have just put those 3 people in a room, right? So there's a difference between having the diversity, so going out there and getting the breadth of thinking you need, and then harnessing the thinking and actually having methods to get people to speak up and make them comfortable to speak up or comfortable to input. That's why I was so rapt when the first time I saw these Miro boards. There are a few people who I know are a little shy, a little quiet, don't really speak up. And all of a sudden, they are like unloading stuff into the space. And I'm like, this is awesome, right? So that was my example. You can have a diverse team, but not be very inclusive.
Yeah. Notwithstanding our failures of the past, why should closure require many more people to be involved? If the operation has been well run, it shouldn't take too long to tidy up the site. I thought your number of BHP staff involved was about right.
That is, yeah, okay. That's a good question. What is the number of geoscientists? I mean, one thing that we do look at is, there's the environmental science aspect of it, right? So there's the monitoring aspect of sites that you have in your legacy assets. And we have a number of legacy assets that we no longer mine, but we still carry liability for. And there's a lot of monitoring that goes on in those. right? So that takes a force of geoscientists to be involved in that. But the other one is that the geoscience, it's about geoscientists being involved in closure even when they're doing the geometallurgical model at the beginning, if you know what I mean, right? So, we're about to open a mine. You're looking at the geometallurgical model. That geometallurgical model is informing what we can do with the processing, which is then informing all of our options for what we're going to do with waste disposal, tailings disposal, and then which then informs, well, how are we going to repurpose this land post mining so that it actually has a positive value for the community? For example, if we've got deleterious elements and they're going to then be, potentially seeping into groundwater, that's going to be an issue, right? And so we're going to have to monitor things. We won't be able to do aquaculture. Well, there's a whole range of impacts. So it's not so much necessarily about having geologists that focus on closure, although I think that will lift. It's more about having geoscience involved all the way through to closure more effectively.
I agree there's significant potential undercover. What do you see as the technology or methodology that has the highest potential to make a stepwise change to our exploration success rate?
Okay, that's the elephant in the room. That one there. The issue is that, okay, I'm going to use an example which I think is really illustrative, and I wish I had the slide up. But if you look at the Gulf of Mexico, Gulf of Mexico is one of the great petroleum basins on the planet, right? And if you look at it in 1960, all the wells pretty much were onshore, right? Then they went offshore, and then there was a break where there was no, in fact, there are very few oil fields. There's a break at the shelf break. And then there's the deeper water, and it's massive, and it opened up progressively over till 2020. So I've got a slide that shows 1960, 2000, 2020, Gulf of Mexico. Now, what opened that up? Now, you talk to people and they'll say it was 3D seismic, or it was deep drilling technology in that, but really what it was a combination of three things. It was concepts. Without the idea, no one goes there, right? So you got to have the idea first, and that's systems, understanding mineral systems. Just getting the inkling that, hey, I think there could be something big out there for these reasons, right? The second thing is, how would I see it? Like, how can I actually go it's undercover, it's 400 meters down. How am I going to see it? Like soil geochemistry, so a lot of my technology package isn't going to help me, right? It's under post mineral cover. What am I going to do? How am I going to see if the elements of the system are there? And then the third thing is that, okay, you think it's there, you think you can see it. It's being able to cost effectively delineate it and then extract it, right? So the Gulf of Mexico was a story of systems and technology. So the first was they did suspect that the systems went offshore. So the first one was technology. How do I this line of sight to ships? So they had a trail of ships to the drill rig, actually physically sighting where the drilling should be. Then GPS and all these types of things open up. Then at that break, at the shelf break, is just where the systems ended. And going into the deeper water, the first thing was the idea that there was actually petroleum systems down there and that they were worth anything, because a lot of people didn't believe it. So mineral systems or petroleum systems actually drove people to think, we think there could be really high quality concentrations of oil down there, and they could be quite big. In fact, they end up being the largest. And that was a big surprise to a lot of people. And then it was, well, how are we going to de-risk this? If we're going to spend $250 million on a drill hole, how are we going to de-risk it? Well, that takes you into 3D seismic. That takes you into all the processing, the ability to quantify the rock mass. And then, well, how are we going to drill and produce it in deep water? And that, so it's a combination of prediction technology, systems, detection technology, in this case, largely geophysics, and then production combined with petrophysics, and then technology for extraction, right? And that's what's going to unlock undercover resources, is that type of similar combination: prediction, detection, discrimination, and extraction.
Well, thank you so much. I'm so glad my persistence paid off and got you on. It's been an incredible session. So thank you so much for joining us, and yeah, being so generous with your time. Yeah, it was wonderful, and hopefully I can get you to come back sometime.
I want to thank the group for the conversation. That's been really good, and also to everyone who listened in, just for their patience. So.